Hi! Today we're going to talk about electric circuits. Behind me you see a very complex and very well-known example of an electric circuit, a motherboard of a computer that possibly you have seen already before when you opened your own computer, or you may want to do at some point just to see what it looks like. So what do we see in this electric circuit? We see lots of different components and we see lots of lines between them. And between those components, what happens? Currents flow, energy gets dissipated and voltages are distributed. So this is what we're going to talk about today. So what is an electric current? Basically, an electric current is the flow of charges through a material. And formally stated, the current is the change of charges dq over time, dt. What is very important to realize about currents is that there is charge conservation. And charge conservation is one of those important conservation laws in physics that tells you anything that comes in has to either way stay or go out. It cannot miraculously appear, neither can it miraculously disappear. So anything that goes in, goes out. This is called the continuity of electric currents. And this is also depicted in the picture below, where you can see that, for example, I1 and I2, they have to be the same, simply because there is no way out or no way in of current, and there's no place to store charges. And so the same statements you can make about I3, I4 and I5. Basically, the current of I1 goes all the way before the crossing to I3, and then it splits into two cases. So some part of the current will go into I3 and the other parts will go into I4 and I5. So this is about currents. So what can happen to currents? So basically what Mr. Ohm, Mr. George Simon Ohm, found out also in the 19th century. 19th century is really the century where all these discoveries about electromagnetism were made. And what he did just like Mr. Coulomb. He built a very simple setup where he had a very controllable resistance, and he investigated what would happen for this constant resistance if he changed the current or if he changed the potential. And by doing that, he found his Ohm's law, which basically states that the current is the voltage V, or the potential, over the resistance, which is a very useful law. And not only that, there is another way to formulate this. It is basically saying that R, the resistance, is 1 over G. And G comes from Geleitung, but in English it's actually conductivity. So the resistance is given in ohm, named after its finder, Mr. Ohm. But the conductivity, G, basically has its unit Siemens. And Siemens is, especially for the electrical engineers among you, he is the founding father of basically the whole field of electrical engineering, due to many inventions he made. And not only that, he also is actually the founding father of the company Siemens. So in that way, I guess he's a real role model for us TU-based students and researchers. Okay, so this is the resistance and the conductivity. So what happens, how can we play with resistors? So one way to play with resistors, as we saw on the motherboard, is we can put them in series. So for example, in this case, you see on the beginning, you see electromotive force, this is the epsilon. So this is basically the battery, and then we can, in series, so behind each other, we can put two resistors, R1 and R2. So now if we think about what happens to the voltage, if we go through the circuit, we can again think of the analogy of the mountain. So with the mountain, what idea is at the beginning of the battery, we're on top of the mountain, which is basically we have added a lot of potential energy. And then if we go through the circuit, we basically go all the way down to the bottom of the mountain. And this way we have dissipated energy. Typically with resistors, this leads to them heating up. If we think about it going through these resistors, we can notice that if we look at the potential, simply the total resistance of the two resistors can simply be summed, can be added. So this leads us to the law that says, if we have resistors in series, they can simply be summed up. So what if we have resistors in parallel? If we have resistors in parallel, what happens is that if you think again of the mountain, you start from the top, but the river, the current basically splits, goes through two lakes or resistors or what you want to call it, and then goes down the mountain. And if you think of that analogy, it becomes obvious that the voltage over the two resistors is the same, but the current is split. And then if you use Ohm's law, you will figure out that if you put resistors in parallel, you can reciprocally add them up. And this means it's 1 over the total resistance of parallel is the sum of 1 over the resistors. And this is in principle not very complicated, but it's not that easy to calculate with. So therefore, if we work with complex circuits with many parallel components, sometimes it's more useful to talk about connectivity. So this is the G again, where for connectivity, we can again say the total connectivity of the system is actually, you can just simply sum up the connectivity of the individual components. So how do we use those laws now? So if we want to simply analyze a simple circuit, we can, that is depicted over here, where you basically have a battery. You first go resistance A, then you go to the two parallel resistors B and C, and then you close the circuit. So if we want to know the potential and the currents through the different resistors, we can go through the following workflow. First, you can determine the current of the entire circuit. This you do because you can calculate resistance, the total resistance of A, B, and C, using the two laws I just told you. If you know that current, you can calculate with Ohm's law the potential, the voltage over A. And if you've done that, you know what's the voltage drop over B and C, and use that to calculate the current through B and C. So basically in this way, you use the fact that the potential for circuit components in series adds up, the current for circuit components in parallel adds up. If you have a current through a circuit component in series, it's the same, and if you have a voltage difference across circuit components in parallel, it is the same. So these are simple rules you can use to analyze a circuit. However, things may become more complicated, and this is also what Mr. Kirchhoff realized. And Mr. Gustav Kirchhoff is a very interesting guy. He also lived in the 19th century, but he was ambitious. So only when he was 21 years old, he was still a student, he phrased Kirchhoff's law. What Kirchhoff's law basically, it realizes charge conservation and says basically the sum of all currents going into a node always has to be 0. And that means there cannot be charge created at the node or charge can be lost at the node. And this is a very powerful relationship you can use to solve circuits. And I guess it seems obvious by now that Mr. Gustav got a Nobel Prize for that. So if you want to be ambitious, I guess you have only a few years left. So what if you have just calculated you made all your calculations, you followed all those advices, and now you think you know the current and the potential through your components. Now how do you know you're correct? And of course, when I was still a student many years ago, I would ask my electrical engineering friends, because I came more from physics, and we would say, yeah, we are going to calculate it and it's correct. And he would say, no. What you do, you plug in the resistance, and if it burns, you are wrong, and if it doesn't, you're sort of okay. So I thought this was an interesting perspective, but maybe sometimes you can be a little bit more subtle, and then what you do is you measure it. So in this case, you can use a voltmeter that you place in parallel with your component, because the voltmeter has an infinitely high resistance, and then you can measure the voltage through your object, may it be a lamp. Or you use an ammeter. An ammeter measures the currents, and therefore needs to be in series, and therefore also needs to have a sort of approximate a 0 resistance, and if you put that in 0, you'll measure the current through your components. Okay, so with this, I come to the end of this unit. I thank you for your attention. I wish you good luck with your examples and exercises.